Hello dear children, welcome to this crash course. The chapter on which we solve problems now is current electricity and of course atoms and nuclei. Example 1. Potential difference across the terminals of a battery is 50 volt when 11 amp current is drawn, and it is 60 volt when 1 amp current is drawn. The EMF and the internal resistance of the battery are. Okay. You know that the internal resistance of a battery is given by E minus V divided by I. So, in the first case, we can write R1 is equal to, this is given by E minus 50 divided by 11, and in the second case, R2 is equal to E minus 60 divided by 1, but R1 and R2 are equal as they correspond to the internal resistance of the same cell. So, what do we have? We have E minus 50 divided by 11 is equal to E minus 60 divided by 1, and this gives us E is equal to 61 volts. And we can choose the first equation. Internal resistance R, which is equal to R1, is E minus 50 divided by 11, 61 minus 50 divided by 11, that gives us internal resistance R is equal to 1 ohm. So, 61 volt and 1 ohm are the values. C is our correct choice. Example 2. The internal resistance of a cell of EMF 2 volt is 0.1 ohm, is connected to a resistance of 3.9 ohm. The voltage across the cell is, the voltage across the cell is nothing but the terminal potential difference, which is given by E minus IR. So, we can simplify it further. E, what is the value of E? EMF is given as 2. The internal resistance is 0.1, and the current is given by E by R plus R into R. So, 2 minus 2 divided by external resistance is 3.9 and this is 0.1 into internal resistance is 0.1. So, upon simplification you get this as 1.95 volt. So, the terminal potential difference is 1.95 volt. Example 3. In the given circuit, it is observed that the current I is independent of the value of the internal resistance R6. This is R6 here. Then the resistance values must satisfy. So, you notice in this problem that this is actually a Wheatstone's network. Let us represent it. R1, R2, and we have R5, that is R6, and this is R2 and R4. So, if this is independent of R6, it simply implies that it is a balanced Wheatstone's network. If it is a balanced Wheatstone's network, we have R1 by R2 is equal to R3 divided by R4, or R1 R4 is equal to R2 R3. So, which is our correct choice? Next one. When a wire of resistance R is stretched and its radius becomes R by 2, the new resistance will be. Initial resistance R1 is equal to R, and that is given by rho L divided by A pi into R whole square. And the final resistance is R dash rho into. You notice that the length becomes L dash and the radius becomes R dash. Because volume remains constant, we can write L1 A1 is equal to L2 A2. L1 R1 square is equal to L2 R2 square, that is pi R square. So we can write resistance R is directly proportional to L inversely proportional to R square. Or we can write resistance R2 divided by resistance R1 is equal to L2 by L1 into R1 square divided by R2 square. So you can simplify this and get resistance R2 is equal to, or R dash is equal to, initial resistance R1 into, what is it going to be, into 2 to the power of 4, that becomes 16. So the final resistance becomes 16 times 16R. Next one. An ammeter reads up to 1 ampere. Its internal resistance is 0.81 ohm. To increase the range to 10 amps, the value of the required shunt is. So it is an ammeter which can read up to 1 ampere. Its internal resistance is 0.81 ohm, and to increase the range up to 10 amp, the value of the required shunt is. So the shunt resistance required is given by I G into G divided by I minus Ig. You have a galvanometer of resistance G and you want the value to increase to I, and therefore to increase its value or say range, you connect a shunt resistance in parallel, and the shunt resistance is given by Ig into G divided by I minus Ig, where Ig is the initial current and I is the final current. So it's going to be 1 into 0.81 divided by 10 minus 1. So this becomes, you can simplify it further. How much is that? 0.81 divided by 9, that is nothing but 0.09. So 0.09 ohm is the shunt resistance required. Next one. 12 wires of equal length and same cross section are connected to form a cube. If the resistance of each of the wire is R, then the effective resistance between two diagonal ends would be. One of the standard questions which is asked quite frequently in the competitive examination. So we can show the construction like this. Now let's assume that a current I enters here, the current gets distributed equally here, we can say I by 3 each, and this current which comes here gets distributed equally again I by 6 each, and the current here becomes I by 3 as this I by 3 and another I by 3 join here, I by 6 join here, I by 6 and I by 6 become I by 3. So I can write the current I into effective resistance between the terminals A and B, this is between A and B, is equal to the sum of the potential difference along its path. So I am considering the journey from A to B along this path, A to X, then to Y, then to B. So A to X to Y to B. So what is the potential difference? I into R effective. That is nothing but I by 3 into R plus I by 6 into R plus I by 3 into R. So the potential difference is same regardless of the path we choose. So what is it we get? R effective from this equation becomes 5 by 6 R. Therefore, the net resistance between the body diagonal of this cube is 5 by 6 R. Example 9. N cells, each of EMF E and internal resistance R, send the same current through an external resistance capital R whether the cells are connected in series or parallel. Then, okay. So, the current when connected in series is NE divided by NR plus R. This is in series. Likewise, the current is same in parallel also. What is that? E divided by R divided by N plus R. This is in parallel. And these two are equal to each other. So I can write NE divided by R plus NR is equal to E divided by R plus R divided by N. So you notice that this E and this E get cancelled and we get N divided by R plus NR is equal to N divided by R, NR plus R. That means R plus NR is equal to NR plus R. This equation is valid only when R is equal to R. Thus, the answer for this particular question is external resistance and internal resistance are equal to each other. B is our correct choice. Example 10. Two wires of the same material and same length are connected to the two gaps of a meter bridge. The balancing length measured from left is 25 centimeter. The ratio of radius of the wire in the left gap to that in the right gap is, okay. So here, you know that the resistivity depends on the nature of the material of the conductor, right? And therefore, we can say resistivities are same. Now, he says same material. So, resistivities are same. You know that rho is given by R into A divided by L. That's right. So, rho 1 and rho 2 are equal to each other. That gives us R1 into pi R1 square divided by L1 is equal to R2 into pi R2 square divided by L2. As length L1 and L2 are equal to each other, we have R1 square divided by R2 square is equal to R2 divided by R1. R1 square divided by R2 square is equal to R2 divided by R1. Now let X be the balancing length. Now if X is the balancing length, then we can write R1 divided by R2 is equal to X divided by 100 minus X. This is 25 by 75. So R1 divided by R2, you know, is R2 square divided by R1 square is 25 by 75, and this simplifies to R1 by R2 is equal to root 3:1. Therefore, the ratio R1 by R2 is root 3:1. That is option C. Next one. When a current is divided between two resistors according to Kirchhoff's law, then the heat produced is. So let us consider the two resistors which are in parallel. This is the construction R1, R2, and let's assume that the currents are I1 and I2. We know that I1 divided by I2 is R2 by R1 in parallel combination. And the heat produced, is given by I1 square R1 T plus I2 square R2 into T. This is, I can simplify it further as I1 square R1 T plus, if the main current is I can write I2 as I minus I1 whole square R2 into T. So now the heat produced is, according to the question, he says the heat produced is minimum, maximum, etc. Now if the heat produced is minimum or maximum, then dH by dt is equal to 0. So we can say I1, if I differentiate and simplify, I get I1 by I2 is equal to R2 divided by R1. So if the currents are in this ratio, or if I put this equation here, I get dH by dt is equal to 0. What does it mean? It means that the heat produced is either maximum or minimum. I can take the second differential and cross check, and if the second differential turns out to be positive for this value, it implies that the heat produced is minimum, which indeed is the case here. So heat produced is minimum. Next one, resistors N each of R ohm when connected in parallel combination give an equivalent resistance of R. If these resistances are connected in series, then the new combination would have a resistance equal to. Okay. So first they are connected in parallel, they give an equivalent resistance of R. Same are connected in series later. So we can say in parallel the equivalent resistance is R divided by N, while in series combination this is NR. Rs divided by Rp is equal to clearly N square R divided by R, or this is N square. So the resistance when connected in series, N square times that in parallel. Example 13. A galvanometer of 50 ohm resistance has 25 divisions. A current of 4 into 10 to the power of minus 4 ampere gives a deflection of 1 division. To convert this galvanometer into a voltmeter having a range of 25 volts, it should be connected with a resistance of, okay. The resistance to be connected to convert galvanometer into a voltmeter is given by V by Ig minus G. Value of V is 25 and this Ig is the current through the galvanometer minus this. Now he says current of 4 into 10 to the power of minus 4 amperes produces a deflection of 1 division. How many divisions are there? So what is the number of divisions? So number of divisions is 25. So 25 into 4 into 10 to the power of minus 4 should give us the maximum current through the galvanometer, that is the value of Ig. So I can substitute this Ig here, and this gives me 2450 ohm. So 2450 ohm. So remember, you are converting this into galvanometer into voltmeter. So what kind of combination it should be? Obviously series combination. So 2450 ohm in series. Next one. A cell of negligible resistance and EMF 2 volt is connected to series combination of 2, 3 and 5 ohm. The potential difference in volt between the terminals of 3 ohm resistance will be. So the potential difference delta V or V is equal to I into R. And now, what is that current? So, current I is equal to 2 by 10. And what is the resistance? 3. So, the potential difference is 0.6 volt. Example 15. An infinite sequence of resistance is shown in the figure. The resultant resistance between A and B will be when R1 is equal to 1 ohm and R2 is equal to 2 ohm. Okay. This infinite ladder network can be converted into a finite ladder network by the following argument. This is R1, these are all R1 each, these are all R2 each, and this is point A, this is point B. Now, I can retain the first segment and replace the rest of the segment by its equivalent resistance. If the equivalent resistance between the end points is X, then the remaining part of the network also has the same resistance, as addition or removal of one segment does not change the equivalent resistance in an infinite ladder network. So, I have R1, R2, and this is resistance X, and between A and B also it is X. So, you know, R2 and R are connected in parallel. So, this is going to be R2 X divided by R2 plus X. You have R1 here connected, and therefore, the resistance between these 2 points being X, X must be equal to R1 plus R2X divided by R2 plus X. You know the values of R1 and R2. R1 is 1. So, 1 plus 2x divided by 2 plus x, and this gives you a quadratic in x. X square minus x minus 2 is equal to 0. And we can simplify this further, and upon simplification you get x is equal to 2 ohm or x is equal to minus 1 ohm. But the negative value is not possible for resistance, and thus this is rejected, and we select x is equal to 2 ohm as the correct option. So, B is our correct choice. Some problems on atoms and nuclei. Example 1. The minimum orbital angular momentum of the electron in a hydrogen atom is. Angular momentum is given by nh by 2 pi. N is equal to 1 gives you minimum value. So, L minimum is equal to h by 2 pi. C is the correct choice. Example 2. According to Bohr's theory, the ratio of the times taken by the electron in a hydrogen atom to complete one revolution in orbits corresponding to ground and first excited states is. The time period is directly proportional to n cube and inversely proportional to z square. So, you can write T1 divided by T2 is equal to N1 by N2 cube, and this corresponds to the same value of Z because it is still hydrogen atom in both the cases. So, this is 1 by 2 cube, or this is 1 by 8. 1:8 is our correct choice. C is the option. Example 3. An orbital electron in the ground state of hydrogen has an angular momentum L1, and an orbital electron in the first orbit in the ground state of lithium has an angular momentum L2. Then what is the relation between these two? Angular momentum L, which is given by nh by 2 pi, is independent of Z. It's independent of Z, which means that L1 and L2 must be equal to each other. So what is our correct choice? A is our correct choice. Example 4. In the Bohr model of the hydrogen atom, let R, V and E represent the radius of the orbit, the speed of the electron and the total energy of the electron respectively. Which of the following quantities are proportional to the quantum number? Let us try to understand what he is looking for here. He says R, V and E represent the radius, speed and the total energy. He says which quantities are proportional to quantum number. Okay. Suppose I consider the product VR. This is proportional to Z by N into N square divided by Z. V is proportional to Z by N, R is proportional to N square by Z. So this is proportional to N. Second, RE. This is proportional to R. E is proportional to N square by Z. E is proportional to Z square by N square. So this is proportional to Z. Third one, V divided by E. V divided by E. So this is proportional to V, is proportional to Z by N, while E is proportional to N square by Z square. This is divided by this term, remember. So this actually becomes N square by Z square. So Z square by N square in the denominator becomes N square by Z square, and thus it is proportional to N by Z. And the last is R divided by E. This is proportional to R, is proportional to N square by Z, and in the denominator we have E, and therefore it is Z square by N square, or it becomes N square by Z square. This is proportional to N to the power of 4 divided by Z cube. So which quantities are directly proportional to the quantum number N? We have the first and the third, that is VR and V divided by E. So V, that is A is, first is correct, and the third is also correct. So what is our correct choice? First and the third. So C must be our correct choice. Example 5. With the increasing quantum number, the energy difference between the adjacent levels in atoms. The difference between the adjacent levels in atoms. So this is, ground level, and this corresponds to N is equal to 2. And if you look at this equation, this is minus 13.6 electron volts divided by N square. So the gap goes on decreasing as you go to the higher quantum numbers, or say principal quantum number. So the gap goes on decreasing. A is our correct choice. Example 6. Two radioactive substances X and Y initially contain equal number of nuclei. X has a life of 1 hour and Y has a half-life of 2 hours. X has a half-life of 1 hour, this is half-life, and Y has a half-life of 2 hours. After 2 hours, the ratio of activity of X to that of Y is, okay. Activity can be written as A naught divided by 2 to the power of N, where N is the number of half-life. So I can write here AX divided by AY is equal to A naught divided by 2 to the power of 2 by 1 divided by A naught divided by 1 by 2 to the power of, that is A naught divided by 2. This entire term is 2 actually. This entire term is 2. 2 divided by 2. Or I can write a naught and a naught cancel, 2 to the power of 2 by 1 divided by 2 to the power of 2 by 2. This is nothing but 1 divided by 2. Thus, ax by ay is equal to 1 by 2. Example 7. The count rate from 100 centimeter cube of a radioactive liquid is C. Some of the liquid is now discarded. The count rate of the remaining liquid is found to be C by 10 after 3 half-lives. The volume of the remaining liquid in centimeter cube is. Okay. The initial activity per volume is equal to C by 100. Count rate is basically the initial activity per volume. Now let V be the volume of remaining liquid. Therefore, final activity after 3 half-lives is C by 10 divided by V. A is equal to A naught divided by 2 to the power of n. So let us plug in this data. So this is C by 10 divided by V is equal to, this is C by 100 divided by 2 to the power of 3 after 3 half-lives. That gives us V is equal to C by 10 divided by C by 800, or this is nothing but 80 centimeter cube. So 80 centimeter cube is the volume of the remaining liquid. Example 8. Half-lives of two radioactive substances A and B are respectively 20 minutes and 40 minutes. Initially, the sample of A and B have equal number of nuclei. After 80 minutes, the ratio of the remaining number of A and B nuclei is. So we can write n is given by n naught divided by 2 to the power of n. Therefore, Na divided by Nb is equal to n naught divided by 2 to the power of 80 divided by 20 whole divided by n naught divided by 2 to the power of, what is it going to be, 80 divided by 40. That gives you 1 by 2 to the power of 4 divided by 1 by 2 to the power of 2, or this is nothing but 1 divided by 4. So the answer is 1 divided by 4. The ratio of remaining number of nuclei of A and B is 1:4. C is the correct choice. Example 9. The decay constant of a radioisotope is lambda. If A1 and A2 are its activities at times T1 and T2 respectively, the number of nuclei which have decayed during the time T1 minus T2 is. So A1 is equal to lambda n1 and A2 is equal to lambda n2. Therefore, n1 minus n2 is equal to, what is it going to be? It is nothing but A1 minus A2 divided by lambda. Therefore, the number of nuclei which have decayed is nothing but A1 minus A2 divided by lambda. A1 minus A2 divided by lambda, C is the correct choice. Example 10. A radioactive sample has a half-life of 5 years. The probability of decay in 10 years is. So number of half-lives is T divided by T, and that is 10 by 5, which is 2. And n divided by n naught initially is 1 by 2 to the power of 2, that is 1 by 4. It corresponds to the initial. And n dash divided by n naught is equal to 1 minus 1 by 4. So the probability of a decay is n dash divided by n naught, which is 1 minus 1 by 4, or this is 3 by 4. So the probability of the decay is 3 by 4, or if I convert it into percentage, this turns out to be 75%. So the probability of the decay is 75%. Example 11. A nucleus with mass number 220 initially at rest emits an alpha particle. If the Q value of the reaction is 5.5 million electron volt, calculate the kinetic energy of the particle. It is the particle which is ejected. So the kinetic energy, which is K1 plus K2, which actually is your Q value, is 5.5 million electron volt. Now from conservation of linear momentum, I can write 2K1 into, this is 216 m under root should be equal to 2K2 into 4m under root. What is this 216m? This is the mass of the remaining nucleus. What is this 4m? The mass of the ejected particle. So momentum of the remaining part and that of the ejected part must be same. So I have K2 is equal to 54 K1 from this equation, or K2 is equal to 5.4 million electron volt. We know the value of K2, so I can go to the equation 1 and simplify to get K2 5.4 million electron volts. B is our correct choice. Example 12. In the options given below, let E denote the rest mass energy of a nucleus and N a neutron. The correct option is okay. So now if you look at this, there are a couple of equations here. Remember, the rest mass energy of U will be greater than the rest mass energy of nuclei into which it breaks. The constituent nuclei and the neutrons will have kinetic energy also as a result of conservation of linear momentum. So what does it mean? If you look at the equations, the one that is most possible corresponds to the one where the final particles or the decayed particles will have kinetic energy, and the neutron which is decayed will also have kinetic energy, and therefore A is the most appropriate choice here. A is our correct choice. Next one. 4 different radioactive elements are kept in separate containers. In the beginning, the container A has a 200 gram atom with a half-life of 2 days. B has a 20 gram atom with a half-life of 20 days. And C has a 2 gram atom with half-life of 200 days, and D has 100 gram atoms with half-life of 10 days. In the beginning, the maximum activity exhibited by the container is. So, activity is given by lambda n. That's nothing but 0.693 n divided by T. That means the activity is directly proportional to n and inversely proportional to half-life. So now if you look at the value of n by T for various containers, which has the highest value? So 200 divided by, in the first case for A, it is 200 divided by 2. For B, it is 20 divided by 20. For C, it is 2 divided by 200. While for D, it is 100 divided by 10. So clearly, A has the highest activity. Example 15. Example 15. Find the wavelengths in a hydrogen spectrum between the range 500 nanometer to 700 nanometer. Okay, the energy of a photon of wavelength 500 nanometer is E is equal to hc by lambda, that is 1242 electron volts nanometer divided by 500 nanometer, and this is 2.48 electron volts. And the energy of a photon of wavelength 700 nanometer is 1242, this is 1242 electron volt nanometer divided by 700 nanometer. So how much is that? This is equal to 1.77 electron volts. You know, the energy difference between the states involved in the transition therefore should be from 1.77 electron volts to 2.44 electron volts, 2.48 electron volts. That gives us n is equal to 3 to n is equal to 2 falls in this range. Correspondingly, this falls in this range, 2.48, 2.44 electron volts, and the other value, which is 1.77 electron volts, lies in this range, 3 to 2. And therefore, lambda is equal to hc divided by delta E. What is that? 1242 electron volts nanometer divided by delta E is 1.9 electron volt, and that is equal to 654 nanometer. So the corresponding wavelength is 654 nanometer. So with this problem, we have come to the end of this discussion. Practice all these problems and be familiar with your equations. All the best.